Hello, this is checkpoint 4.36. They want us to use the problem-solving strategy to find the absolute max and min for this function to find the extrema, absolute extrema. So we have a function 4x squared minus 2xy plus 6y squared minus 8x plus 2y plus 3. And the given domain is x goes from 0 to 2 and y goes from -1 to 3. I think it would be good to start off by drawing out that region on the xy plane and identifying what it is we're dealing with here. So 0 to 2 for x values and -1 to 3 for your y values. And we have this rectangular region. Everything in here, and also including everything in the boundary, could possibly be your max and mins. And so the strategy is to find our critical points and identify all the critical points that are going to be within the boundary, and then find critical points within the edges, and then the corner points. So it could potentially that we have at least 4 points to check. Those are the corners, and any other critical points inside, and any other critical points that might be on the line. Okay, let's get started by finding the critical points. We can do that by finding the partial derivatives. This is going to be an 8x to the first power minus 2y with respect to x, that's 0, and we have a -8 and zeros for the rest. We're going to set this equal to 0, just as we're going to set the partial derivative with respect to y equal to 0. It's going to be a 2x plus 12y plus 2. And if we set these equal to 0, we can factor out a 2. We get 4x minus y. The 2's factored out. Minus 4 equals 0. So we get y by itself. Y equals 4x minus 4. Here we're going to have -x plus 6y plus 1 equals 0. We'll put in the y that we got. We get -x plus 6 times 4x minus 4 plus 1 equals 0. And that would be -x plus 24x minus 24x plus 1 equals 0. So that's a 23x. Oops, this is a 24, sorry. Minus 23 equals 0. So we'll bring the 23 on the other side. X is equal to 1. And when x is equal to 1, we're going to get y is equal to 1, 4 minus 4, which is 0. Okay, we have identified one point, and that point happens to be within the region. And let's call this point A. And for point A, we have 1, 0, and we want to know what the y value is. And the algorithm or the strategy tells us that for the critical points inside and on the boundaries, as well as the endpoints, they want us to put those into the function to see which one's the largest. So we put 1 in for x and 0 in for y. That's going to give us a 4 minus 8, that's -4. -4 plus 3 is -1. Okay, that's our first point. Now we need to check the boundaries. So within the boundaries, we have to identify which boundary we're dealing with, find out possible max and mins on the boundary we're dealing with, and then check them. So the first boundary we'll look at would be the boundary where x is equal to 0. That seems like a good place to start. When x is equal to 0, we'll put that into the function, and we'll end up getting a function of y. So 0, 0, we get a 6y squared plus 2y plus 3. That is our function. And now within that function, we want to find out if there are any critical points. And this is just really a function of y, but technically f is a function of two variables, so let's take the derivative with respect to y. That's 12y plus 2. We'll set that equal to 0 and get y equals to negative 1/6. So y is equal to 0, y is equal to negative 1, or x is equal to 0, y is equal to negative 1/6. And let's figure out what the z value would be, and that's putting the function, putting negative 1/6 in for y, and that's going to give us the original function we're looking at. Let's see. There we go. That would be 6 times 1/6 squared plus 2 times 1/6 plus 3. I think a common denominator of 6 would do. Would be 1/6 plus 2/6 plus, oops, this is a negative, so let's put a negative here. This will remain positive, but this second term would be negative. And this is going to be an 18/6. So that's negative 1, that's 17/6. Okay, that gives us our y value, or our z value. So let us come back over here and note that on the domain it's 0, negative 6. Let's call that point B. And if we put point B into the function, point B was 0, negative 1/6. We ended up getting 17/6. Okay, we have a minimum and a maximum so far. And now let's just check to see if there are other points to consider. Next in line that we should try, we don't have to do this in the particular order that I'm doing it on, but we'll look at the x is equal to 2 line, and we'll write x is equal to 2 here and do the same sort of analysis. So we have 2 in for x, and y is still a variable. So if we put 2 in for x, we're going to get 16 minus 4y plus 6y squared. 2 in for x minus 16 plus 2y plus 3. What do we get? I think the 16s cancel. We get a 6y squared minus 2y and plus 3. Now, just like we did before, we're interested in analyzing critical points. And so we'll take the derivative. Again, y is your variable. This is 12y minus 2. We set that equal to 0. And we're going to get a positive 1/6 this time. So we got a positive 1/6. X is equal to 2. That's going to be our point in a domain. We'll look that up in a minute. But we should, since we do have a critical point, it would be good to figure out what is happening at that critical point when we put positive 1/6 into the function. And we'll use this function, or we can use the original function, but this is already the function we already put the 2 in, and this is the function part where we simplified it already. So let's use that. 6 times 1 6 quantity squared minus 2 times 1 6 plus 3. And I think this is going to be the same calculations as we had in the previous one. So we got 17 6. Okay. On this edge, we got a 2, comma 1 6. We'll label that point C. And you got the function that's 2 comma positive 1 6, and we ended up getting the same number. Okay, so that's 2 edges. Let's do 2 more edges. Our next edge that we're going to consider is down. Let's consider this one where y is equal to -1. So shrink this so we can see the original function. And here we'll do it y is equal to -1. So we have a function of x, a y of -1, and that would be a 4x squared. Y equals -1. This will be a positive 2x. Y is equal to -1. We'll have a plus 6 minus 8x. Y is equal to -1. Let's do a minus 2 plus 3. All right, let's focus in on that, analyze that. Critical points. Before we do that, let's simplify. We got a 4x squared. This is going to be a minus 6x. And 9 minus 2 is 7. Now let's take the derivative, this time with respect to x. We get 8x minus 6. We set that equal to 0. We're going to get x is equal to 3/4 positive. And we got y is equal to -1. That is our point on the domain. And to get the actual point, we'll put that f of 3/4 -1 into the function. We got 4 times 3/4 quantity squared plus 6 times 3/4 plus 7. And the 4 here would be 16. They'll cancel with one of the 4s. This will be a 9. 9/4. 18/4. And why not just have the same denominator? 28/4. And oops, except this should be a negative. Let's make that correction. -6 over here, so that means this should be -18/4. All right, that's going to give us a positive 10 plus 9, 19/4. Okay, big picture. We found a 3/4 comma -1. That's within the boundary. A, B, C, let's call this point D. And our point D here, we'll put 3/4 in for x and -1 in for y, which we already did. We got 19/4. Okay, so 17/6 is a little bit less than 3. 19/4 is a little bit less than 5. So I think right now we have a maximum at the point D, but let's figure out what happens on that last boundary. And for this one, let's use purple. This is y is equal to 3. And so when y is equal to 3, We're going to put that into the function. X is still a variable, y is 3. So we have 4x squared. Y is equal to 3. This is going to give us a minus 6x. Y is equal to 3. That's 9 times 6 is 54. 8x. Y is equal to 3. We'll have a plus 6 and plus 3. Okay, let's focus in on this and analyzing it. Let's simplify it first. We got a 4x squared. This is a minus 14x. And then that's 60 plus 3 is 63. Okay. Derivatives to find the critical points. This is 8x minus 14. Set that equal to 0. X is going to be 7 over 4, 7/4. 7/4 is within the boundary of x being 0 and 2, between 0 and 2. So 7/4 is in between there, which means that's a valid point that we need to check. Let's figure out what happens when we put 7/4 in for x and 3 in for y. So we have a 4, and you got 7/4 squared minus 14 times 7/4 plus 63. Cancel 7/4. 7 squared is 49 over 4 minus, this is going to 7 times 14 is 96, 98 over 4, and 63 times 4, 12, 4 times 6, 24, 25, 252 over 4. Let's see, 49 and 98. I think that's negative 49. Subtract 49 from 52. We get 203. So let's get 203 over 4. This so far has been the largest value. Let's see if it'll stay that way. First, let's put this in our graph. Big picture point of view, 7/4, comma 3. That's close to 2. Let's call this point E. F of 7/4, comma 3, and we got that to be 203 divided by 4. So this is around 50, a little bit short of 50, like 49.75 or something. Okay, so far that's the maximum. Well, those are the 4 sides that we're looking at. And now we actually need to check 4 more points. We need to check these 4 points. Okay. We can label them. Where are we? E. Let's call this one F. Let's call this one G. Let's call this one H. Let's call this one I. So E, F, G, H, I. Got lots of points to check. Oh, we have 4 more. So F is X is 0, Y is -1. For G, X is 2, Y is equal to -1. For H, it's up here, 2, 3. And for the last one, I, 0, 3. Okay, putting 0 in for X and -1 in for Y. We're going to get 0, 0. This is going to be 6 plus, putting -1 in, 6 minus 2 is 4 plus 3 is 7. putting 2, -1 in, 2 in for x. This is going to give us a 416. This will give us a positive 4. So that's 20 plus 6, 26. 26 plus 16, 32. Well, I think I'm losing count here. Well, if you put it in the calculator, I think we're going to get 11 for that one. And why don't we just say that I worked it out and I got 63 for this one and 51 for that last one. Okay, those are the values, and we find the minimum and the maximum. So the minimum looks like it's that critical point that we found, and the maximum looks like it's one of the corners that we found. So let's label that as a max. Okay, so we're pretty much done. I think it might be good to take a quick look, take a peek at the graph. I do have a graph of this here, labeled here. I first plotted this function, and I had to play around with the limits for your x and for your y and for your z. I had to squish z down quite a bit, and because it went all the way up to 63, as we saw in our analysis. And so I scale factored the x and the y so that are a little bit, that makes the z more compact. And I plotted the points as well. The critical value point was the red point. You can see it disappear and appear again. And the high point was the one with a 63 as a z value. And so you can see that appear and disappear again. And everything else are the values that we found. So let's take a quick picture of this and send it to our notes so we can analyze it a little bit and draw on it. So we can see where those points are. We have looks like the blue points are the ones in the corner. So this is, I think, hard to tell now because it got rotated several times, but we know that the minimum here is the critical point, and the minimum was at the point x is equal to 1, y is equal to 0, and z is equal to -1. And the maximum was up here, and that was the point 2, 3, 63. Okay, all these other points look like they are minimums. The critical points that we saw looks like they're minimums for within that particular boundary, but in the big picture overall, they did not become the minimum or maximum. Okay, so that's how we go through the process. And first we identify your domain, and then we find the critical points. So here at this step we found critical points, and then we checked as many edges as we need to do. So here we had 4 of them to check, and they correspond to each of these edges, and for each of those we found points that could potentially be max and mins. And then finally we check the endpoints, and then within all those points we plug it into the original function to see if we have a maximum or a minimum. All right, I hope that helps. Good luck.